In this lecture, I want to talk about how to find some basic derivatives. Recall that this is the derivative of f with respect to x. This is a function, and it'll give us a function. When we do this, it'll give us a function that we could use to find the slope of the tangent line at any point x in the domain of f. Well, to be more specific, any point x in the domain of f where f is differentiable. Remember from our last lecture that this is what we had to go through. So we had this specific function here, f of x, and you see down here, this was all the work that we did to get the derivative. So I think it's important to understand the definition of the derivative because it has some connection. It has some connection to kind of graphically what's going on, to understand that that's the slope of the secant line, and we take the limit, we get the slope of the tangent line. But it's a little bit cumbersome, to say the least, to have to use the definition every time we want to find the derivative of a function. So in this lecture, I'm going to talk about some shortcuts, basically, ways that we can find the derivative without having to use the definition every time. So first is a constant function. So this is something along the lines of y equals 2, or we could call it f of x equals -5. But, whatever it is, the point is it's a horizontal line, right? So this is y equals 2. And if I use another color to denote, we'll go way down here and call this, f of x. I'm using y and f of x interchangeably, but the point is that the slope of any tangent line to this line, will be this line, right? And what's the slope of this line? Well, the slope of any horizontal line is 0. So if this is y, then y prime is 0. Or if this is f, then f prime is 0. So for any constant, the derivative of a constant is 0, and it's because we can think of it graphically because our tangent line will always be horizontal to a horizontal line. It's really that simple. This is actually a special case of any linear function. All right, so if we think about any linear function, so if we have a line, let's say it looks like this. I don't know. Let's give it. Let's say 1, 2, 3. I don't know. Let's call it y equals 2x plus 3. Then any tangent line to this line will have the same equation as this line. So we're not necessarily as interested in what the equation of the tangent line is when we want the derivative. In other words, if I want y prime, I want the slope of a tangent line to this line. But the slope of the tangent line, I could try to draw it on there, right? Like, let's say I wanted to find the slope of the tangent line here. A tangent line would actually just be right on top of it, right? It would just be the same line. If it has the same line, then it has the same slope. So for this, y prime would be 2. If I had, for example, f of x equals -3x plus 5, then f prime would be -3. So we can see, whatever the slope is of a linear function, the derivative of a linear function will be equal to that slope. All right, just a very brief kind of proof of that. If we had y equals mx plus b, let's go ahead and use our definition to show that y prime would equal m, whatever that slope is. So we take the limit, so y prime equals the limit as h goes to 0. And so remember, it's going to be, it's f of, I'm going to go ahead and write it, f of x plus h over f of x over h. But this y is our, that's our f of x. So what we're going to have is m, and I'm going to replace x with x plus h plus b minus f of x, which is just mx plus b over h. All right. So here I can distribute, so I have mx plus mh plus b, and I can also distribute this negative both to the mx and to the b, so I have minus mx minus b, and this will clean up quite nicely for us because mx minus mx is 0, and b minus b is 0, so I'm just left with mh over h, but h divided by h, of course, is 1, so there you have it. And notice that the beauty of a more general derivation like this is that we know it works no matter what our function is. So no matter what our slope is, we know that the derivative of a linear function will be just the slope. All right? Okay, those are a couple to get us started. I want to show you just a more general way to find the derivative of anything of the form x to the n. So x to some power, and this is called the power rule. So again, using our definition, so let's say this is f of x equals x to the n. I'm going to use this definition, so I'm going to have the limit as h goes to 0 of x plus h to the nth power minus x to the nth power over h. Alright, so it doesn't really look like we can do much with this right now. The trick is to expand this using the binomial theorem. So I'm just going to go ahead and give that to you, but I think it's worth seeing this once. The result is very nice though, and it's something that we will use quite a bit. So this is going to be x to the n plus n choose 1, this is a combination, n choose 1, x to the n minus 1 times h, plus n choose 2. I'm not going to get into exactly, we could actually, this can be reduced and we can figure out, for any value of n, we could figure out what that number would be, but it would be the coefficient here. But I don't want you to get too hung up on that. I just want you to see the form here because what comes out is pretty amazing. Then we have n choose 2, x to the n minus 2, h squared, and we don't know what n is, so we can just kind of keep going. H cubed. One thing to notice is that these powers always add up to n, right? This is n minus 1, this is h to the first power. You can think of this as x to the n and h to the 0 power, so they always add up to n. And we can kind of keep going here, and then we kind of get toward the n, and we have n choose n minus 1, and now it's x to the first power, h to the n minus 1 power, and then finally n choose n, which actually we could also think of this as a n choose 0, which is just n. Which is just 1, and this is also 1, and then this is just h to the n. So that's that whole thing expanded, and then I have this minus x to the n, that's all in the numerator, over h. Alright, so what can we do here? Well, like I said, n choose 0 is 1, so this is x to the n, and this is minus x to the n, so those are gone. N choose 1 is n, and that's important, so I'm going to write that one down. That's n times x to the n minus 1 times h, plus all this other stuff. N choose 2, x to the n minus 2, h squared. I'll leave this one out. Plus, we keep on adding these terms. This actually is also n, so that's n, x, h to the n minus 1, finally plus, and then n choose n is 1, and that's just h to the n over h. Now, due to this cancellation, notice that every other term here, that's n, and this is h. We should make clear which is which. But every term up here has an h in it, so let's factor an h out. If we take an h out, then I've got n x to the n minus 1 plus n choose 2 x to the n minus 2 times h plus all these things, and then I'm going to have here, so I'll have n x h to the n minus 2, since I took one out, plus h to the n minus 1, again, since I took one out. So I just factored an h out of all those. This is all over h. The reason I factored that is now this h and that h cancel, right? So we're just left with 1. So finally what I'm left with is this, which is n x to the n minus 1 plus n choose 2. Well, I know if this is tedious for me, it's got to be tedious for you. But let me just finish this up here and we'll see what we get, because like I said, the result is a very nice one. So this is what I end up with after I simplify this up here. So this is as far as I can go. Now I'm going to take the limit as h goes to 0. But this is continuous with respect to h, so I can just put in, and everywhere I see an h, I can put in 0. But notice, all of these terms now, this goes to 0, this goes to 0. Every term except the first one becomes 0 because all of them have an h in them. And we're just left with n times x to the n minus 1. And that is the power rule. This is f prime. Right? So let me just use another color to try to highlight this. Because this is, if this is f, this is f prime. That may still look a little alphabet soup to you because we're still doing a bunch of numbers, or a bunch of letters. But let me just give you a specific example of this. We've already spent a lot of time looking at x squared, right? And we have found this one the hard way. So this is n, right? So remember, the derivative, just to kind of keep this up here with us, is n times x to the n minus 1, right? If f of x is x to the n. Another way of thinking about this is I take this n out front and multiply by the exponent, and then I reduce the exponent by 1. So in this case, f prime would be 2 times x, and then I subtract 1 from 2, and I'm just left with x to the first power, which we don't usually write, right? We just write x. If I had, just do f of x equals x to the 4th, then f prime of x is 4x cubed. Bring that 4 out front, and then reduce the exponent by 1. What about, maybe I use a different letter, how about g of x equals square root of x? This is one that we've also worked with and had to kind of beat our head against the wall to make that one come out. How does the power rule work here? Well, we can rewrite that as x to the 1/2. Those are equivalent. Now I can use the power rule. So that's going to be, I'm going to take the derivative. It's 1/2 x to the, now 1/2 minus 1 is negative 1/2, right? Now that might not at first look like what we found. Remember before we found the derivative of that to be 1 over 2 square root of x. Let's see how these are equivalent. Well, that's 1/2, and then we can rewrite this as 1 over x to the 1/2. But x to the 1/2 is square root of x, so that's 1/2 times 1 over square root of x, which I can multiply numerator and denominator. That's 1 over 2 square root of x. So that works, all right? How about something like 1 over x squared? All right. Now, what a lot of students will want to do is they'll want to say, well, that's h prime of x is 1 over 2x. It doesn't work like that. All right. It has to be of the form x to a power, not 1 over x to a power. So this is not right. Don't do it. All right. What we need to do is rewrite this as x to the negative 2. If we do that, now we can use the power rule because now we have something of this form. So now h prime would be negative 2x, and this is where you got to be careful with your negative numbers. Negative 2 minus 1 is negative 3. And if you like, you could rewrite that negative 2 over x cubed. Notice that is not anything like 1 over 2x. Okay, don't do that. Rewrite it. Rewrite x with a negative power and then use the power rule. So in general, I would strongly encourage you, anytime you can rewrite something in this form, as x to some power, do it, because the power rule is probably the nicest tool we have in terms of finding derivatives without killing ourselves. All right, a couple more things that will be helpful to us. If we have f plus g, two functions added, and we wanted to find the derivative of them, then it's just f prime plus g prime. And this goes back to the fact that the derivative is a limit. So all the rules that we had for limits, remember we said that the limit of a sum is the sum of the limits provided that each of those limits exist. Likewise here, this is true as long as f and g are differentiable. If they're not differentiable, then all bets are off. But But ultimately, all of this kind of just follows from our rules for limits. So if I have two functions that are added, then the derivative is, so let's give you a quick example. What if I had, you know, x squared plus x cubed, and I wanted to take the derivative of that? Well, that's just going to be the derivative of x squared plus the derivative of x cubed. That's just 2x plus 3x squared. All right, so there's an example. Also works for subtraction. All right, that would work just as well. So if they were subtracted instead of added, same deal. All right, how about another one? Let's look at a constant times a function and take the derivative. Remember, when we're taking limits, the constant can come outside of the limit. So same thing, because the derivative is a limit, then I can rewrite this as the constant times the derivative of the function. So again, another example, the derivative with respect to x of, I don't know, 8x to the fourth. All right, well, that is going to be equal to 8 times the derivative of x to the fourth. All right, this we can just use the power of rule for very simply. So that's 8 times 4x cubed, which simplifies to 32x cubed. Now, I wanted to do this to kind of show you how this works, but ultimately notice what I could have just started up here, and I could have done 4 times 8 to get 32 and then reduce the 4 to a 3. So here I'm kind of being real technically correct that I have to take the constant out and then take the derivative and multiply the constant back. But when you have something like this, I think it's simpler. Just multiply and reduce this by 1. Okay, just to kind of give you one example where we're putting this all together, let's call f of x 7 over x cubed plus x squared plus 5. All right, and we want to find f prime. All right, well, this rule up here tells us that I can find the derivative of the sum by just taking the derivative of each of these pieces separately. So this one I want to rewrite as 7x to the negative 3. And then using this piece right here, I can just say negative 3 times 7 is negative 21x, and I'm subtracting 1 from negative 3, that's negative 4. Now this one, we've already done that one, that's 2x, and 5 is a constant, so it goes away, all right? We don't, it's a, you can say plus 0 if you like, but we don't usually do that. So you can see the derivatives get a little bit easier. You can imagine how much fun it would be to use the definition to find that one. And so these rules derived from the definition can really be helpful in finding derivatives. All right, last one. I just want to show you how to find the derivative with respect to x of e to the x. This is one that we'll see quite a bit. So I just want to go through the derivation of how we get this derivative. So this is going to be using the definition, limit as h goes to 0, of e to the x plus h, right? That's f of x plus h. We just replace x with x plus h minus e to the x over h. All right? That's just, again, just as a reminder. Let's see if we have it over here. That's using our definition. Since f is e to the x plus h is f of x plus h. Now, remember that this could be rewritten as e to the x times e to the h, right? If the base is the same, then when I multiply, I can just add the exponents. And I'm going kind of the other direction and pulling them apart, all right? And then that's minus e to the x over h. Why the heck am I doing that? Well, I want to factor out an e to the x here. So if I take out e to the x, I'm left with e to the h minus 1. Notice if I distribute that back, I get this back exactly over h. Now here's the thing. I'm taking the limit as h goes to 0. So anything that doesn't have an h in it, we can think of as a constant, right? It doesn't move. It doesn't change. This right here is not going to change when h changes because there's no h in it. So I can rewrite this as e to the x limit as h goes to 0 of e to the h minus 1 over h. Now, some of you with good memories will remember that we actually investigated this during the very first lab. We investigated it graphically and numerically, and maybe it was the second lab. But either way, the point is we've played with this a little bit before. I'm not going to prove it, but you can investigate this graphically and numerically. You would see that this seems to approach 1, which leaves us with the very nice result that the derivative of e to the x is e to the x. If only they were all that easy, then, well, we probably wouldn't have a class called calculus. Okay, so that is an important result, that the derivative with respect to x of e to the x is e to the x. So quick example here, let's say we had a function that was 9 plus 2 e to the x, then the derivative, well, the derivative of any constant is 0, and here the derivative of 2 to the x is 2 times the derivative of dx, which is just 2 e to the x. All right, so those are some handy little rules that will help you to find the derivative of common functions. Then we will get into some other rules that will help us when we're looking at products of functions or quotients of functions or combinations of functions. But this was, like I said, like the title advertised, these are just basic derivatives. Constant function, linear function, the sum of some functions. The power rule was an important one. So these are just some kind of tools, some tricks in our bag to help us find basic derivatives.